And our next probe, guaranteed to get every engineer all excited. Oh, it's the active FET probe. And they always come in impressive cases like this and this and this. Right? You never just get like a little like probe in a packet, whatever. No, they always come in beautiful cases like these. Let's take a look at them. So here's a very typical active probe, or the active FET probe, or just FET probe, because they've all got FETs right at the input here that actually amplify the signal before it comes in. So they have active amplifier electronics inside the head, as opposed to your passive probe here, which is just basically a bit of a resistor and a bit of coax, and the amplifier is inside the scope. Well, in this case, the amplifier is up here, which means they have to actually be supplied by power. And it's very common for them to actually be powered from the oscilloscope under test. And look at these, lovely little pogo pins. And you usually buy them from the manufacturer of the oscilloscope, because they've got their own interface. This one is your Agilent Keysight. So those probes not only give it power, but they also, tell it what type of probe it is and things like that. Your signal doesn't actually come out on these pins. This is just power and other data. Your signal, of course, goes into your input to your scope. So it's just, that's a regular BNC, but it just plugs in, it's all captive, and they usually have a little lever in there to clamp on the front of your scope. So these things are usually very pricey. They start in the 4-digit category and go up to like 5 digits. And this one here is a 2 gig bandwidth probe, 10:1 divider ratio, 1 meg input impedance, and this Siglet one here, active probe, it's 1 gig with 1 meg ohm and 1.2 picofarads. But you might think, well, okay, this is 1 gig. Well, so is this. What's the difference? Well, the difference is, remember, this is like practically the world's best passive probe, 3.9 puff. This one, 1.2 puff. And that's the difference. You remember our formula before. Capacitance is the thing that matters at high frequency. And in the case of this Siglet active probe compared to this Tektronix one, both are 1 gig rated probes, but because it's only 1.2 puff, it's 132 ohms at 1 gig, whereas the passive probe is 40 ohms at 1 gig. So that can make a heck of a difference to the signal that you're actually measuring. That load is going on the line that you're trying to probe. So the lower the capacitance, the less you're going to load your line. But if you are talking DC, then the passive probe's still better. That's 10 meg at DC. These are only a meg. So you'd use an active FET probe over your passive probe when signal integrity at high frequency really matters. Well, A, these can go higher. This is actually the fastest passive 10:1 passive probe you can get at 10 meg. And as I said, this thing with a resistor will, if you build it right, will actually outperform this, and these can actually go up to 10 gig. So anyway, so the only solution basically for above 1 gig measurement is either an active FET probe or a resistive probe. That's it. And if you're wondering, this Agilent one is 1 puff input capacitance, and this one here, haven't measured it, but it probably be on par, something like that, in the order of a puff, half a puff maybe. So the great thing about active FET probes is they can actually go beyond 10 gig and beyond the performance of a simple resistive probe like this. So if you're on the bleeding edge of measurement, you're really going to be wanting an active FET probe. So pretty much, as a ballpark, maybe anything over 500 meg, you want to either be using an active FET probe or a properly built and characterized resistive probe. And it can cost you more money to actually characterize this than to simply buy the already characterized active FET probe. And basically, these single-ended active probes pretty much stop at a couple of gigahertz. Anything over that, then you start talking a fully differential probe, but not high voltage like we looked at before. These would be low voltage differential probes, high speed, low voltage. But the one downside with these things is Murphy can get really expensive. Like, these probes can cost thousands of dollars, even into the 6-digit range, and their huge Achilles heel is the maximum input voltage. In this case, max input, 20 volts peak, okay? Seriously, you go over that, and this probe will blow up. You'll probably find eBay's filled with this FET probe, sold as is. I would not be buying a sold as is FET probe off eBay, just saying. We've got one from Caltech Electronics here. This one's a little bit more robust. We're talking 40 volts peak here. It's a 1.2 gig probe. Once again, 10 to 1. This one's higher input capacitance though, 3 puff. But as you can see, this one, you can get like generic ones. You don't have to get these ones designed for your specific scope. You can get these cheaper ones that just plug into your, like any scope, and they're just actively powered, once again, from just the USB port on the front of your scope. Nice. And as I showed before, these things always come with like all these accessories. Let's take a look at them because they're very interesting. So these are the ones that come with the Caltech probes. You've got beautiful little ultra tiny mini grabbers there. You've got little ground and probe pins like that, spare ones because you're going to be using them all the time. Plus you've got like little pins like that that you can plug into headers. And often on your designs, if you know you're going to be probing like really serious designs, maybe on a prototype board, you don't necessarily need it on a production layout, but on a prototype board, you're trying to get it working, you're measuring your high speed DDR bus or whatever, then you might have dedicated test points on there, even dedicated connectors for these high speed probes. And the Siglent ones, once again, you get all these like spare tips because you're going to be going through them like there's no tomorrow. You might even want to directly solder the tips into your circuit so that you can physically remove your probes. But the most interesting kit comes with the Keysight one. Once again, you've got a little tube with all the little pins in there. Geez, they don't give you many, do they? A bit of a tight ass, real expensive probe. You get ultra tiny mini grabbers. Once again, like these things are just super, super tiny. And then you like plug into there and give you all sorts of other little adapters like that. And the most interesting thing is they give you copper pads like this, and they actually give you a bit of a chart here on some of the different probe connection techniques. And this is not the video to go into really high frequency probing techniques, of course, but you can look, you can plug directly into the head with some long leads like that, and that'll give like 500 meg bandwidth here, they're saying, or you can get a rigid probe tip with offset ground like that, so it plugs in. And I love this Keysight head. It's got little LEDs on there that just light up so you can see where you're actually plugging your probe into. Very nice. And then you've got a spring tip with ground blade like this, and that'll give you like 2 gig bandwidth. And then you've got a copper pad which you can solder onto your circuit, and that will give you like a flexible ground point. So often it's very difficult to apply pressure to like both of these points at the same time without one of them sliding around. Well, if you solder in like a large ground pad like with that copper tape that they supply, then you don't have to worry about your ground probe sliding around, or you do have to keep an eye on it because Murphy and Shaw will slide off and short out one of your other pins, something on your expensive $100,000 prototype board. Trust me, I've worked on $100,000 prototype boards, and if you blew that up, yeah, you're going to be having a bad day. But once again, that might be a slightly reduced bandwidth to, this technique over here, which is going to provide a lower inductance path. So it's going to, you're going to get better performance out of it, something like that. And then you just got, if you want to put just pin headers on your board for various test signals, and then little short cables which run over and just plug into your probe tip. So all these different solutions for probing, and you can even invent your own. And as I said, a lot of designers will solder on like coax connectors directly onto the board and things like that. So you can plug on your own probes, your own resistive probes or active FET probes, or whatever it is you're doing. So active FET probes, you can think of those as the Rolls-Royce of oscilloscope probes, really. They're very nice, but as I said, roll your own with a bit of RG174 coax, and well, you can get similar performance if you do it well enough, but oh yeah, these can't be beat if you got the money. And these probes will usually require 50 ohm termination on your scope, although this Caltest one here, it comes with a 50 ohm terminator. Look at that, 2 gig, 50 ohm series inline terminator, 2 watts. Oh, that's very nice. But this one actually lets you use it with a 1 meg input impedance scope, just so you know 50 ohm termination. And it gives you an actual attenuation setting of 5 times, so that's better for like low signal measurements. Nice. Okay, let's give you a probing example here. We've got a Raspberry Pi 3 for those playing along at home, and we're going to probe one of the memory pins on the bottom here. I don't care which one. I've just picked one at random. We're getting a signal on it. So I'm using the 2 gigahertz active probe here, the N2796. Overkill for what we're doing. Well, overkill for this scope anyway, because this is a 500 megahertz bandwidth scope. So this active FET probe, more than good enough for measuring the bandwidth that we got here. So I'll use this long lead here for my ground. I'll put it on the ground pin of the connector there, because that's just very convenient. For those who care about such things, you can actually see what point I'm probing. Where is it? I think it's there. Geez, I can barely see that. This is where, you know, magnification comes in. Okay, I'm probing a point there. I don't know what it is. I don't care. There it is. There's our signal. It's made up of a whole bunch of stuff, but basically you can see, look, it's got some undershoot here. It's got a little bit of ring in there. It's got a little bit of ring in there. I'm going to hazard a guess that that's going to be due to our long ground lead there, right? So that is our thing, but we've got actually higher frequency stuff in here. Look at this. Oh, I just happened to capture one there. Look at this. It goes down, up. We're at, what, 10 nanoseconds per division. We're almost as fast as we can get here with this scope. But this actually does have some really fast pulses in here. So something, you know, the bus is switching. It's doing whatever. I don't know what point we're probing. Check that out, right? There you go. Because that looks very sinusoidal. We're talking about, that's our sine X on X interpolation there. So this is like, sort of, once you see that, you know, okay, we're beyond the bandwidth of our scope here. These signals are just too fast. But anyway, let's just go back to here. Okay, so we'll just try and capture that sort of like the most frequent one there. There it is. Got it. Okay, so I'll store that. Right, so what I'm going to do now is I'm going to actually change the ground into this. Instead of having this longer lead, I'm going to go for one of the shorter little ground adapter pins we've got in there. And it looks like there's a little bypass cap. I've determined that this right-hand side is the ground. So that's very convenient because that's right next to the point that I want to test. Otherwise, as I showed before, like you might have to like install one of those copper pads or something. You might have had to like scrape away some of the ground here or something like that and maybe put the copper tape over the top of the chip or something like that. Or you'd have to scrape away some other ground point somewhere, or, you know, soldering a little contact loop pin or something like that. So here it is. I got my little adapter. Careful, because you can stab yourself with these little bastards. There we go. So we have this little now ground pin, which can sort of like, you know, pivot around like that. And anyway, that will make better contact, and this will be a higher frequency probe because it's a shorter inductive path. So let's try that. We'll require the tongue at the right angle and probably some magnification here. Okay, I've got my ground point and I've got my probe point. Pan up, pan up. Okay, let's have a look. I've changed my digitizer, definitely getting 5 gig samples per second, and I saved my reference waveform. So let's single shot capture that, see if we can get it. No. There we go, got it. Now I can actually adjust that waveform there to show you. There you go. So the orange one I've got there is the reference waveform, and this new yellow one is the one that we just probed. And there you go. It is like, it's of course like the same wave shape. You can see it's got the longer ground lead one. The orange one has some extra undershoot there and comes back and takes more time to come back up like that. And the one up here got some extra wiggle, 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 yeah, on the top there, some overshoot. And so, you know, there are differences in probing right there. But at the moment, this is the loading of the line with a 1 picofarad, 1 puff active probe, which costs a couple of $1,000. Okay, now I'm going to use my 500 megahertz passive probe here. It's the N2843. It's 11 picofarads, okay? And yes, I've compensated this. You compensate it with your probe compensation on the front, so everything's hunky-dory. I'm using my low inductance, high frequency ground probe attachment, so that's equivalent to what we had before. So we should get, because we've only got a 500 bandwidth scope here, then the bandwidth of the probe isn't really going to matter that much. Hold my tongue at the right angle. and probe this. I think I got it. But here's the interesting thing. I've changed the reference waveform to my low inductance short ground one before, so the orange one is the best we could get with our active probe. So the exact same ground point, basically the same ground length, and you can see that, well, you know, our wave shape's the same, but look at this. It's a much higher level down here. Okay, this is 200 millivolts per division, so it's like, you know, 50 odd millivolts higher there, and it's actually lower down here, our yellow waveform there. So, you know, although we can see like the wave shape and everything up here, it's like when the bus is loaded differently, because that's what this little, you know, ramp up here is going here. I don't know the architecture of the Raspberry Pi. It doesn't matter, but I know there's something happening there with there. And down here, we're actually seeing a larger drop across the bus here, which is interesting, isn't it? You know, there's significant differences here. This wasn't the exact example I wanted to show. I just, like, it's a random example, but you can see the difference here between a 500 meg passive probe and effectively, because of the bandwidth of the oscilloscope, a 500 meg active probe. They load down the circuit differently. And I know you want to see it. Okay, let's compare Dave's dodgy homemade resistive probe here with a 1K resistor in the tip. We'll give that a whirl. Got a 50 ohm terminate that, but scope can do that, no worries. Tongue at the right angle, tongue at the right angle. Fix that. Oh! Oh, check this out. This is absolutely fan-freaking-tastic. Now, what we've got here, the orange waveform, of course, is our reference active FET waveform. That's a $2,500 active FET probe. Yes, it is compensated, because you do still have to compensate them, and it stores it internally because it knows the serial number of the probe, etc. And the yellow one is Dave's do-it-yourself couple of buck resistive probe. Look at this. What's going on here? Well, it's obvious that what's happening at this point right here is that the bus is actually going open or something. I don't know the exact architecture of what's, you know, the pin I'm actually probing. It doesn't matter, right? It's like it's going open. And because the probe is 1 meg DC resistance, look at that. It's not going to discharge. Maybe if we got like a longer time period, it'd eventually do a similar, like eventually discharge or whatever. But you see that the bus has actively changed. But because we're now loading this bus down with a 1K resistor or a 1.05K resistor, because we've got the 50 ohm terminator as well, boom, this looks like, for all the world, and it is, an RC discharge curve. So there you go. What's that? You know, 10 nanoseconds per division. I don't know. You can work that out, whatever, for those playing along at home. But you can see how the resistive probe actually completely changes the circuit that you're actually measuring. So sure, like the signal integrity is excellent. Let's take a look at this actually. If you have a look at the bottom here, you can see that both of them undershoot almost exactly the same. But you remember how I said that the resistive probe can actually be more tolerant of longer ground leads. I think they're both about the same length. I think they're practically near identical. Remember how I said it can be more tolerant on these than active FET probes? This might be an example of this, because this is not, this is not some controlled experiment. This is just something I slapped together willy-nilly, and this is the result that we actually got. This is fascinating, right? They both undershoot exactly the same, but the active FET probe, the orange one, actually, look, it overshoots again and it takes much longer to recover than the resistive probe. Look at that. So this could be an example of where this cheap-ass do-it-yourself resistive probe is actually outperforming this $2,500 active FET probe in terms of signal integrity. But once again, this is not a completely controlled experiment, but this is what you can actually get. But of course, the limitation is that it loads it down much more, 1K as opposed to 1 meg, right? There's a huge difference there. And you might know, oh, what's the difference between this load? You know, look, it's dropping with the 1K. Is that the effect of the 1K load over here? If we actually measure that, because you remember, it's a divide by 21 probe as opposed to the active FET probe, which is divide by 10. So if we actually set up our cursors here, and I've set them precisely to the same ground point here. Our resistive probe is, we're getting 55 millivolts there. So if you get your confuser out, 55 millivolts times 21, which is our probe, 1.155 volts. And this is it looks like it's a 1.2 volt bus. So it's it's maybe 50 millivolts under, but we have to measure the other one actually. So if we adjust that, we're talking about 60 millivolts there. So it's actually precisely 6 divisions there, and we were on 200 millivolts per division, so that's precisely 1.2 volts. So the resistive probe is actually measuring 50 millivolts less, and that could be the extra loading of the 1K load. You'd have to check out the driving strength of the driver actually used in this, which is the whatever micros used on the Raspberry Pi or whatever. We can see that it's basically 50 millivolts under. So that could be like an extra 50 millivolts drop caused by the loading of the probe. That's what it seems to be the case. But once again, this isn't exactly a really proper setup controlled experiment. And by the way, no, this is not just a like a freak capture where the bus did something different than before. This happens every single time. No matter how many times I capture this, the 1K probe is definitely totally different to the active FET probe here. And you can see, obviously, the bus was floating there, and then it went boom. No, I'm going to go actively low.